All right. Hello, everybody, and welcome. It's time to start your journey into multivariable calculus, and I am super excited to be the one that's going to get to help you along this journey. Um, I'm going to have all of my lectures pre-recorded, and I'll post them on my YouTube channel, but make sure you watch these lectures before you come to class, and we will do activities related to this content in these lectures in class. I'm going to go ahead and pull up the slides. You can find the slides on our course's Canvas shell. So if you go to Canvas, you can download the slides, you can follow along. There are links to the slides, links in the slides, all sorts of good stuff. But let me pull them up now and let's get started. Okay, so we're still using the same book that we used for Math 7 and Math 8. That's Calculus 1 and 2. The book is Calculus by Stewart, Watson, and Clegg. It's the ninth edition. It's the late Transcendentals version. These sections and these lectures follow the sections in that book. So you can always use that book as a reference, and the homework is pulled from that book as well. These slides are slides that I created, and I modified things quite a bit. So there's extra things that I want to talk about, some things that I kind of gloss over, but it's all really fun stuff. So before we can begin talking about multivariable calculus, the very, very first thing we need to do is talk about higher dimensional space, in particular, three-dimensional coordinate systems. So that's where we're going to begin. One sec, let me change this. There we go. Yes, okay, nice. All right. So here's an overview. We're going to quickly review the Cartesian plane, which is R2 or R cross R. Then we're going to talk about three-dimensional space, and we're going to talk about having an eye toward higher dimensions in all of this class. So we'll get there when we get to it. We'll explore some very simple surfaces. We're going to talk about the use of some really helpful technology, in particular Mathematica. Then we'll talk about midpoints and Euclidean distance and finish up with spheres in space. All right, so here's a quick review. I'm assuming all of you are very comfortable with this. This is just the Cartesian plane, R2 or R cross R. We use the Cartesian coordinate system oftentimes to describe points in this space. There's also the polar coordinate system, which we'll review briefly later on because we're going to use it. And the idea is basically that we use an ordered pair x comma y to uniquely determine and describe the location of a point in the plane. So like here's the point A comma B. Zoom in a little bit there. There's the point A comma B. It's because you go this way, A units in the x direction, and you go this way, B units in the y direction, and that's how we describe this point. All right. The axes meet at a point called the origin. It's 0, 0. And the location of any point in the plane can be described in this way. So if you give me this point up here, I can tell you the exact location of that point. So 3 dimensions is really not much different. So if you want to do calculus in 3 dimensions, you got to be able to describe 3-dimensional space in a rigorous way or a more cohesive way. There's some kind of a way, right? So all we're going to do is we're going to extend the Cartesian coordinate system to 3 or more dimensions. Here's how we do it. 3-dimensional space is just denoted by R3. It's just R cross R cross R. It's basically taking the real line and crossing it with itself 3 times in an orthogonal or perpendicular way. R3 is just the set of all ordered triples, where each one of those coordinates is a real number. That's how we describe it. Just like before, choose a fixed point, call it the origin, and that's going to be the 0, 0, 0 point. And passing through that point are 3 coordinate axes. There's the x-axis right here, the y-axis right here, and the z-axis right here. Because you kind of have to choose an orientation to basically, which way is up? That's the question. So if we're calling this x and this y, which way do you want to call up? Do you want to say this is up or do you want to say this is up? You actually get to choose. So by convention, we like to use what's called the right hand rule, which basically says if you hold your hand like you see in the figure here, and you curl your fingers from the x to the y direction, where your thumb is pointing is what we're going to call up. So that's the positive z direction, like so. So you can kind of see it in that picture right there. And we'll use that throughout the course. All right, so what is a point? So a point in space is just an ordered triple, like so. A is the x coordinate, B is the y coordinate, and C is the z coordinate. Each coordinate represents the directed distance along the respective axes, just like we saw in 2 dimensions. So if this is your point A comma B comma C. It says to go this direction along the x-axis this far, this way along the y-axis this far, this way along the z-axis that far, and then you land at a point. All right, now, because we have we have another dimension now, we actually have some, I'll say, subspaces that are called planes. So there are some really important planes in R3, the XY plane, the YZ plane, and the XZ plane. And they're pictured right here. And what you get, or I should say what these planes are what you get when you set one of the coordinates equal to 0. So for example, the XY plane is just the plane that you get when you set z equal to 0. This is the plane that you've been working in for all of your previous math classes, presumably. What is the xy plane? It's the set of all points in R3 where the z coordinate is equal to 0. And it's right here in the picture. It's the floor. You can think of it as the floor. The xy plane is the floor, and then you have two walls, xz plane and the yz plane. They're described analogously. So what is the xz plane? It's the plane that you get when you set the y coordinate equal to 0. So it's a set of all points where y is equal to 0. And if you look at the picture, it really builds your intuition, right? If this is the y-axis and I set that value to 0, whatever points I want to talk about, then I'm not going to be here and I'm not going to be here in the y direction. I'm going to be right here. But I could go up in the z direction, or I could go that way in the x direction. And so that gives you the xz plane, right? Similarly for the yz plane right here. So the yz plane is just the plane that you get when you set x equal to 0. Set x equal to 0. And those are what we call the coordinate planes. So if you hear me use that term, coordinate planes, that's what I'm talking about. Right, now, one of the things that's really helpful is what are called point projections. So if we've got a point in three-dimensional space, a lot of times we're interested in different projections of that point. You can project it down onto the xy plane, you can project it onto the xz plane, the yz plane, and we're going to see other types of projections in another section coming up here. But if you've got a point A comma B comma C, and you project it down onto the xy plane, then what you get is the projection of the point P onto the xy plane. So notice this point right here is the point ABC. Well, if we project it downward to the xy plane, we're basically taking the z coordinate and making it 0. So then we get this right here. This point Q, that is the projection of P onto the xy plane. There you go. You can also project it into all sorts of other things too. So you could project it onto the xz plane like so. You could project it onto the yz plane like so. Those are just called point projections. Here's some examples. So here's the point -4, 3, -5. How do you locate that point in space? Well, you go this way along the x-axis, -4 units. This way along the y-axis, +3 units. And then this way along the z-axis, -5 units, and you land at that point. And that's kind of the idea. One of the things I recommend to help you build build intuition is to, frankly, look around the room. Like, look around your room. You can pick any corner you want in the room, and you can call that the origin. And then you can talk about X, Y, Z, and you can talk about describing points in your room. And you should just imagine like a point moving around your room somewhere, like floating in space. And that's the kind of stuff we want to talk about. All right, now with all of this, this is one of the reasons I love this class. You really want to have an eye toward higher dimensions, Calculus 3 is really exciting because nearly everything we learn can be extended to any finite number of dimensions. So here we're talking about 2 dimensions, 3 dimensions. What about 4 or 5 or 6, 7, 8, 9, 10, a billion, a trillion, however many dimensions you want? You want to have an eye toward this idea of higher dimensional space because, frankly, a lot of the stuff we learn just generalizes to higher dimensional space. And in fact, some of the most interesting questions in math pertain to infinite dimensional spaces. We won't be talking about those in this class, unfortunately, but some of you will be exploring infinite dimensional spaces, and that's where some of the stuff gets very, very fun. Like, here's a good question, right? Actually, maybe I should preface this question. I'm sure you all know from Calc 2 or Calc 1 or just geometry, the volume of the unit ball in 3 dimensions, right? 4/3 pi r cubed. Oops, there we go. So here's my question. What's the volume of the four-dimensional ball, or the five-dimensional ball, or the six-dimensional ball? And then from there, what could the dimension of an infinite, I'm sorry, what could the volume of an infinite dimensional ball be? It's an interesting question, something for you to ponder. And actually, that reminds me, now that we're here, one of the things that I'll do during the lectures is I will throw up some emoji that should should tell you to basically do what the emoji is doing. So this is a good time to basically ponder and say, wait a minute, what are these higher dimensions? And what does he mean by infinite dimensional space? I got no idea. So now's a good time to like pause and just contemplate these things. So I like to throw up what I call the thinker, just so that you can think about it. Then I like to put up what's called the speaker. Oftentimes during like an example or during the lecture, I'll ask you to think about a concept and then speak about a concept. And the speaking part is really just what's the word? A cue for you to speak out loud. And you don't have to say anything to any person. Just talk out loud to yourself to give your brain that feedback. Our brains really like when we talk out loud and then we hear what we're talking about, and then we're like, wait, does that make sense? No, that doesn't make sense. Does it? Yes, no. So talking out loud, even just to yourself, can help you make sense of things. It doesn't have to be to a person or anything like that. Then I'll often have you do this as well, which is just to write something down. So for some of the examples that I show, I'll ask you to think about it, say something out loud about it, and then write it down, start working on it. All right? Okay, so let's get back to this. Just something to ponder. Volume of an infinite dimensional ball. What does that even mean? Here's another cool thing. The notion of dimension can be extended even beyond integers or positive integers, right? You might be thinking 1, 2, 3, 4, 5. We can talk about arbitrarily real valued and even complex valued dimensions. So for example, in fractal geometry, we talk about non-integer dimensions all the time, all the time. So for example here, log base 3 of 2, that's the dimension of the Cantor set. So if you look up the Cantor set, it's got dimension log base 3 of 2, which is an irrational number, and it's a transcendental number. It's certainly not an integer, and it's certainly not a natural number. You can even talk about dimensions having complex values, and that's actually directly related to my own research in fractal geometry and complex dimensions. So if you want to talk about that stuff, I'm always more than happy to get lost for many, many hours talking about that stuff. So for any of you that want to study fractals, a lot of that investigation and exploration involves thinking about non-integer dimension objects. Okay, so for now, we'll try to temper ourselves. Maybe I'm just speaking to myself here. Temper ourselves a little bit, but higher dimensions don't need to feel alien. They don't need to feel very bizarre. We just simply extend our coordinate system the same way that we did a couple of minutes ago. So we knew what two-dimensional space looked like. You've been working in it for many years. Now we know what three-dimensional space looks like. We're going to work in it for the rest of the course. You can do the same thing to any number of dimensions, and for now we're just going to stick to positive integers to keep things a little simpler. So in general, for any positive integer capital n-dimensional space is r to the n, Rn. And it's just taking the real line and crossing it with itself n many times. How do you describe points in this space? They're called n-tuples. So it's the space consisting of, or sorry, it's the set consisting of all ordered n-tuples, where each one of these coordinates is a real number, and you've got n of them. So R3, R4, R5, R6, Rn. That's the idea. Just a little note at the bottom here. When we get to about 4 or 5 dimensions, we usually like to switch to this subscript notation, just because we don't want to have to deal with a bunch of random arbitrary letters. XYZ works great when you're working in 3 dimensions. XYZT works great when you're working in 4 dimensions. Once you get to 5, you have to kind of start picking letters that you may not want to pick necessarily because they get used for other things. All right. Okay, so now that we have an idea of what n-dimensional space looks like and we've got a coordinate system we can use, we can start talking about surfaces, and we're going to explore these a lot in this class. So what is a surface in space? Well, let's go back down to level 2 for a minute. Let's go back down to two-dimensional space. So in two-dimensional space, the graph of an equation involving x and y is what we call a curve. These are what you've been playing around with for years in math classes, right? Just a curve. In three-dimensional space, if you've got an equation that involves x, y, and z, That describes what we call a surface. So quite literally, just imagine almost like a sheet in space, or maybe like a folded, rounded sheet, or any kind of a thing in space. Like look in front of you, like you're staring right in front of you, and just imagine some surfaces. Then in general, if you want to go up to higher dimensions, in n-dimensional space, we call the graph of an equation involving all of these coordinates, all these variables, a hypersurface. Hypersurface. So this is where you get to learn all the cool terminology, hypersurfaces and stuff, hypercubes, all that fun stuff. That's just a fancy name for that object in higher dimensions. So here's a good example. This is one I want you to try on your own for a minute. I'm going to throw up the thinker in just a moment. What surface in R3, so that's 3 space, what surface is represented by the equation z equals 3? So I want you to ponder this for a minute. Just think about what this means and what this could describe. See if you can visualize it in your head. All right, now I want you to say something out loud about what you were visualizing or what you were thinking this equation describes in space. All right, now let's take a look at it together. So in this case, the equation z equals 3 is describing a plane, and it's a plane that passes through the point 0, 0, 3, and it's parallel to the xy plane. So this is a picture of what that plane looks like. Just a flat sheet in three-dimensional space that crosses the z-axis right there. One thing I want to point out is we specifically mentioned that we're working in 3 space, and the equation z equals 3 only involves one of the coordinates, z. All right? So because it's only involving one of the coordinates, the other 2 coordinates are what we call free variables. That means they can be whatever you want them to be. There's no restriction, there's no condition on what x and y are. The only condition we have is z is 3. So if we're saying z is 3 and we're in three-dimensional space, what does that describe? A plane, this plane right here. So the set of points describing this plane is this. It's the set of all ordered triples such that z equals 3. Every single point on this plane satisfies this condition here. All right. Okay, how about this one? What surface in R3 is represented by the equation y equals 5? So you think about this one. Think about this one for a minute. All right, now say something out loud. What do you think this equation represents in 3 space? All right, now write it down. So see if you can write down what it is. See if you can draw a little sketch. Maybe go back to the previous example and see what the sketch looked like there. See if you could draw a sketch by hand. All right, now let's take a look together. So here, one thing I notice right away is we're working in 3 space, and there's only one variable that appears here, y. So that means that x and z are free variables. X and z can be whatever we want. The only stipulation here is that y is equal to 5. Boom. That's going to describe a plane. It's a plane that is parallel to the xz plane, and it passes through the point 0, 5, 0. In fact, maybe I'll, just to emphasize, this is 0, 5, 0. That's that point right there. And the idea is the same thing as what I said before. It's just in this case, x and z are free variables, and y is the only variable that has a condition placed on it, that it's got to be equal to 5. All right, now, you might have had a little bit of difficulty visualizing these things or being able to sketch them in particular. I highly recommend practicing drawing these things in 3D and just trying to work on your three-dimensional graphing abilities. But you'll notice very quickly that if you want to draw anything that's even, you know, maybe just a little bit complex, it gets really, really hard to sketch them. And, not everybody is an artist. So this is why we have helpful technology. In particular, we have 2 very nice pieces of software, Mathematica and Desmos, which I'll talk about in a minute. So here's a reminder, at least as of the time of this recording, every SMC student has free access to Wolfram Mathematica and Wolfram Alpha Pro. All right. Wolfram Alpha Pro. So you may have used Wolfram Alpha in the past, or you may have seen it or come across it at some point. What I'm saying is if you're an SMC student, the math department already got funding for you to have access to Wolfram Alpha Pro for free. You don't have to pay for it. Wolfram Alpha Pro is great. It's basically the online version of Wolfram's Mathematica software. The downside is it's online, so it doesn't have, I should say, it doesn't have the computing power that your computer does. So Mathematica is basically the desktop version, quote unquote, of Wolfram Alpha Pro. But really, it's that Wolfram Alpha Pro is the online version of Mathematica. So Wolfram Alpha Pro is not as strong as Mathematica. So I strongly recommend that you go and download this right away. We're going to use it extensively throughout this course. We're going to have activities where we go to the computer lab and we program things in Mathematica. All you got to do is go to this website, enter your SMC email address, and you'll get access to that software. I didn't mention it here. I'll mention it out loud at least. One of the great things about Mathematica is that the documentation is extremely well organized and it's all available online. So if you want to download the desktop version of Mathematica and you need to save some space on your hard drive, you don't really need to download all the documentation that comes along with it because you can just go to Google and just like type in Mathematica and the command you're interested in, and the first hit will be the Mathematica documentation for that command. Yeah, so it's really, really, really handy. Yeah, and as our objects of interest get more complex, we're going to need to use Mathematica. We're going to use Mathematica to visualize things. We're going to use Mathematica to calculate things. Mathematica can do pretty much everything that we learn in this class. So what I'll do is I'll try to tell you what commands of interest there are as we go along. There is also Desmos. So I think most everybody is familiar with Desmos at this point. If not, you really got to check it out. Just go to desmos.com. It is a very, very intuitive calculator. And in particular, it's got a very intuitive graphing calculator interface. So for 2 dimensions, it works amazingly. And I use it in all of my classes, really. It actually recently, within like the last year, I want to say, they upgraded their software to be able to graph certain objects in 3-dimensional space. So if you click on this link, it'll take you straight to Desmos's 3D graphing calculator. But that software is still in the beta phase. So even though it is pretty good, it is nowhere near, even if it were, it's nowhere near the capabilities of what Mathematica has to offer. So Desmos is really good if you want to do a very, very quick, intuitive graph of something you're interested in, but it's really not sufficient for what we're going to want to do, which is look at a lot more of the details of the objects we're studying. So I recommend getting comfortable with both pieces of the software, but specifically Mathematica. All right? Okay, here's a question, and this is one that I want you to think about, and then we'll take a look at it together. What surface in 3 space is represented by this equation? All right, the equation x squared plus y squared equals 1. So think about it for a minute. Right, now say something out loud. You can say it to yourself, to your dog, to your friend, to your brother, sister, your cat, your lizard, like whoever, whatever, the wall. Say something out loud about what you were thinking. All right, now write something down. So write down what you think, what surface you think is represented by this equation, and see if you can draw a sketch of it. And then we'll take a look at it together. All right, here we go. So let's see what we know about this already. One thing I noticed right away is this equation looks really familiar. It's the equation of a circle. X squared plus y squared equals 1. That's the unit circle centered at the origin. However, we are working in 3-dimensional space, and I don't see a z in here. That means that z is a free variable, which means z is going to be any possible value. So this describes a circle in 2-dimensional space, but in 3-dimensional space, it describes a cylinder. Oops, here we go. It describes a cylinder. I'll go back to the previous slide in a moment. Here, the stipulation is that you got to be on this circle, but z doesn't matter. So you're on the unit circle, but z can be whatever you want z to be. So you get a circular cylinder with radius 1, and its axis is the z-axis. All right. Yeah. Basically, yeah, exactly. So this is the set of points in space that satisfy that condition. Now, maybe I'll switch the order of these slides. Here's one of the helpful commands that we can use in Mathematica, and I'm going to pull it up and show you what it looks like in Mathematica in just a second here. But this is the command contour plot 3D. If you click on this link, it'll take you to the documentation for that command and show you how to use it, give you some examples, all that stuff. I also like to add some additional formatting options, and you'll see that I actually made them like global options in my Mathematica notebook. But this is the command, contour plot 3D, and then you basically tell that command what surface you want to plot, and then you give it some conditions on the variables. X is between -2 and 2, Y is between -2 and 2, Z is between -2 and 2. That's basically what the command requests. What is the thing you want to describe, and give me restrictions on the variables. The rest of this is actually just formatting because I find that it makes the images a little easier to, well, they look a little prettier. These are not necessary, and I recommend that you mess around with them. And there's literally thousands and thousands of options and thousands of things that Mathematica can do. We're not going to touch even 1/10 of half of a percent of what Mathematica can do. But let me show you what it looks like. Let me switch windows here. There we go. Okay, so this is Mathematica. What I have open right now is a Mathematica notebook. This is the notebook for section 12.1. It's a .nb file. .nb is a Mathematica notebook file. This is just a title cell. There's basically different cells in Mathematica. So this kind of indicates what cell you're on. Right over here, this is just the title. And what I mentioned a moment ago is I like to set some global options for my notebooks just for certain graphs. So here's an example. Here's contour plot 3D. Here's that command. And this is exactly what was just on the slides, right? But instead of including all of the formatting options for this one image and this one command in this one cell, what I did was I just made it a global setting. So anytime I use the command contour plot 3D, I want these conditions on the image, the graphic that it produces. So the command for that is set options. You set the options for this command. Got some commas here. Boxed false means I don't want the box to be outside of it. I can set where the axes are going to be. The labels, in this case, I want the labels to be automatic, and you'll see here that it automatically labels it X, Y, Z. And then mesh none, I basically don't want it to show the mesh that it's using to generate the image. And we'll play around with these in the activities. I'm not going to mess with them right now. But this is what it looks like. So here is that cylinder. And with Mathematica, we can do all sorts of cool stuff. We can tip this, turn it, we can scale it, right? We can get a really good look at it. But here is exactly what that surface looks like. So you can see that it's, if I look straight down on it, we got the unit circle. That's what it is. Now, if I turn it to the side, we can see that the z variable is free, so you get an infinitely long cylinder. Obviously, a computer cannot handle infinity. That's why we have to tell it where to stop. So for example, if I change these, maybe I make this, here we go, -5 to 5. And then if I want Mathematica to run this command, if I want it to evaluate this cell, what I do is I hit Shift Enter. All right, so I'm going to hold Shift and press Return. And there we go. There we go. So now notice Z is going all the way up to 5. Maybe I want it to be even more. 10 to 10. Shift Enter. 10 to 10. Now, it doesn't change the image too much. It's just changing the scale, right? But if you start messing with the scales, you can move all of this stuff around. Maybe you could do X from like, let's make it a not uniform. But yep. Now it looks like an oval, but that's just because I changed the scale of the X-axis. There we go. So maybe we should keep it uniform. -6 to 6. I can't see it. 6, 6. There we go. Nice. All right. Okay, so now let's go back to the slides. Where are you? Right here. Okay, so we'll mess around more with this later, but now we know what a cylinder looks like. All right. Okay, here's another example. Think about this one. What points x, y, z satisfy these two equations simultaneously? So this is another one where I want you to think about it for a minute, and then we'll look at it together. What points could possibly satisfy these equations? What does the image look like to you? All right, now say something out loud to yourself. What do you think this figure is going to look like? Okay, now let's take a look together. One thing we already know is that x squared plus y squared equals 1, that's the unit circle. So because we're working in R3 still, we know that that is going to be that cylinder again, right? It's that cylinder, but now we have an additional condition on z. So we're saying z has to be equal to 3. So we're not talking about the whole cylinder where z was a free variable. We're talking about that cylinder, but also z is equal to 3. And what you get from that is, I'm going to switch here, is a circle. This is what we call a space curve, which we're going to talk about more in section, oh geez, what is it? 13.3, I believe? 13.3. This is exactly what it sounds like. It's the unit circle, but it's centered at the point 0, 0, 3 instead of 0, 0, 0. That's it. So we've got another Mathematica command. I'll go show you in Mathematica in a moment, but this is what that object looks like. Yep. Yes, okay. So one quick thing, the way that I'm graphing this circle in Mathematica is I'm using another command called parametric plot. So parametric plot 3D. And we're just going to use the standard parameterization of a circle. So this is something that you talked about in Calculus 2. You might have talked about it in trigonometry or another math class. But this is basically just parameterizing the circle using the usual cosine and sine parameterization. And we're going to specify that z is equal to 3. All right, let's take a look at Mathematica and see what it looks like. All right, let me go down here. There you go. There's the picture. You can turn it around. Here it is, parametric plot 3D. X is given by cosine of t. This is the x coordinate, or I should say x coordinates. The y coordinates are given by sine of t, and the z coordinates are always 3. There you go. Now, remember, this is parameterized by one variable, t. Sometimes you could think of it as theta, right? So we have to tell Mathematica how far we want t to go. This is like the range for t. So I chose t to go from 0 to 2 pi. Makes sense. So that's one complete rotation around the circle. For example, if I were to change this to just pi and recompile, I get half the circle. The upper half of the circle, you could think of it like that, right? There you go. That probably looks familiar. All right, now turn it to the side. Welcome to Calc 3. Calc 3 for Calc 3D, right? Couple quick notes about Mathematica syntax. For functions, it's got all the functions that you love and know from the past already built in. Sine, cosine, they're already built in. When you want to call a Mathematica function, it uses a capital letter. That's why this is capital cosine. And the inputs, or I should say the arguments of these functions are denoted by square brackets. So let me, like, if you want to do cosine of x or something like that, right, or cosine of t, capital C brackets, and then whatever your variable is going to be. And it's the same thing for all of their functions. You might notice that parametric plot 3D starts with a capital letter and opens with a square bracket, closes with a square bracket. There you go. Okay, now back to the slides. All right. Okay, so now that we've seen what it looks like, let's move on and talk about midpoints and Euclidean distance. So some of the classic formulas that you remember from the past have natural extensions to R3 and just more generally Rn. So this is the good old midpoint formula that you know and love from the past. The midpoint of a line segment from P1 to P2 is given by just taking the average of every one of the coordinates. So x1 plus x2 divide by 2, you end up in the middle. y1 plus y2 divide by 2, you end up in the middle. z1 plus z2 divide by 2, you end up in the middle. And so this is the midpoint of a line segment in R3 from point 1 to point 2. That's basically it. In the past, you probably saw it in 2 dimensions where you would just have this, averaging the x coordinates, averaging the y coordinates, and that's the midpoint. So this idea extends in general to Rn. So if you've got n dimensional space, 1,000 dimensional space, however many dimensions you want, you can still talk about line segments in that space, and you can still talk about where the midpoint of that line segment is. So let's say we want to know the midpoint of the line segment in Rn from this point with these coordinates to this point with those coordinates. The idea is identical. Add up the first two coordinates, a1 and b1, and divide by 2. Then add up the second coordinates, a2, b2, divide by 2, ... repeat until you've done that to every pair of coordinates, and this is the midpoint. That's the idea. All right. Similarly, the Euclidean distance formula also generalizes to three-dimensional space and n-dimensional space, as we're going to see in a moment here. So the distance d from point 1 to point 2 between these 2 points is really just a generalization of the good old distance formula that you remember from a previous class, whether trigonometry or algebra or geometry, Calc 1, Calc 2. You've probably seen it in a whole bunch of classes. So there it is. In the past, you might have seen it cut off right about here when you're in 2 dimensions, right? Well, now we're in 3 dimensions. So we need an extra term here. All right, now, how do you prove it? You try to prove it. I encourage you to try to prove it. It really just follows from the same proof that you remember from learning it in 2 dimensions, which is the Pythagorean theorem. The distance formula really is just the Pythagorean theorem. So if you want to know the distance formula in 3 dimensions, you just apply the Pythagorean theorem twice. So I encourage you to try it. You try to prove it, and then what you can do is you can check out the proof in the book. The proof is in the book in section 12.1. All right. Now, what's cool about this is you now know the Euclidean distance formula for the distance between any 2 points in any dimensional space, any positive integer dimensional space. So in 1 dimension, check this out. If you were just on the line, like the real line, and you wanted to know the distance like between 2 points, right? That's what that is, but notice that's the same thing that you get when you do this. Squaring something and then taking the square root always gives you the positive result. So that's the same thing as taking the absolute value. That gives you the distance between those 2 points. Voila. In R2, this is what you've seen in the past. In R3, we have this. Now, in general, for n-dimensional space, you just do the same thing. You keep adding more and more of these difference terms, and then you add them up, and then you take the square root at the end. And that's pretty much it. Just take the difference between the respective coordinates, square that result, add all those results up, and you get the n-dimensional Euclidean distance function. Naturally, Mathematica has a command for this. So if you wanted to do this quickly or you're working in larger dimensional space, just use the function Euclidean distance. If you want to find the midpoint, just use the function midpoint. And again, if you click on these links, they will take you to the documentation for those commands so you can see them, you can practice them there. That's the idea, just see like all the syntax and examples. All right, now let's try one. You try this one on your own, and then we'll talk to each other afterward and see how it goes. Find the distance between these 2 points, and then find the midpoint of the line segment connecting them. All right, think about how you're going to do it. All right, now say something out loud about how you're going to do it, even if it's as simple as, I'm going to use that formula we just learned. Right? Now work it out yourself, and we'll compare answers in just a minute. See if you can find the distance between these 2 points and the midpoint of the line segment connecting them. All right, here we go. This is really just a calculation. We will use that formula from before. The distance between P and Q is given by this right here, using the distance formula. Do some arithmetic, you get this, take the square root, you get 3. So the distance between these 2 points is 3. What is the midpoint of the line segment connecting these 2 points in space? Take the average of the respective coordinates and you get the midpoint. So we're going to do 2 plus 1 divided by 2, and then -1 plus -3 divided by 2, and then 7 plus 5 divided by 2, and this is the midpoint. One thing you can do if you're interested, go try it on Mathematica. Open up Mathematica, try to use those commands, and check your answer. Be sure that it's actually correct. Okay, now we've talked about a bunch of stuff. Let's finish up by talking about spheres in space. So you should recall from geometry that a circle is the set of points in R2 that are a fixed distance r from another fixed point, h comma k, which we call the center. So the number r is the radius of the circle, and the point h comma k is called the center of the circle. And that's what a circle is. Basic idea is you pick a point in the plane, you pick a radius, and then you talk about all the possible points that are that far away from that center point. Thanks, Notability. That's not quite what I wanted. I'll just stick with my hand-drawn circle. Pretend that's a perfect circle. There you go. So this would be the point h comma k. All right, so how do we generalize this idea to a higher dimensional space? Well, in a natural way, you do the same thing. A sphere, what is a sphere? It's the set of all points in 3 space that are a fixed distance r from another fixed point called the center. So now that we've got 3 dimensions, we have ordered triples. So our point consists of 3 coordinates. H, K, and then L is another common letter to use for the third coordinate. R is still called the radius of the sphere, and HKL is called the center of the sphere. So everything else is the same. Right. Now here's a good question. See if you can find an equation of a sphere with radius R and center HKL. Right? So here we have the definition. This is like the geometric definition of a sphere. This is how it's defined through pure geometric intuition. My task that I'm giving you is, can you come up with a formula for it, an equation in X, Y, and Z for the sphere? All right? Think about it for a minute. All right. Now say something out loud to yourself. What do you think you could use? Use your intuition. Think about how you could use your intuition. Right, now work it out on your own. See if you can work it out, and we'll compare answers in just a moment. Okay, here we go. All right, so you might recall, let me go back to 2 dimensions. It always kind of helps to go down to 2 dimensions to gain intuition about the third dimension. I remember when talking about circles in the plane, the formula was what? It was this, right? X minus h squared plus y minus k squared equals r squared. Yeah, and again, this is basically the distance formula, right? Imagine if you did this, now you have the distance formula. It's all connected. All right, so if I needed to generalize this to 3 dimensions, I suspect it's going to look like this. And sure enough, that is exactly what it is. There we go. That's it. So that was just how I came up with it using intuition and thinking about generalization, right? To make things a little bit more rigorous, you can use the definition the same way that we use the definition way back in like Calc 1 or pre-calc to find the formula and the equation of a circle, right? So if a sphere is the set of all points that are a fixed distance away from the center, all that means is that this distance is fixed. So if we square both sides of this, we get the formula. And that's it right there. Distance between P and any of these points and the center is R, right? What is the distance? Well, we just use the distance formula, square both sides, and boom. That's the formula. If we are fortunate and the center of the circle happens to be at the origin, things simplify very nicely. If h comma k comma l is 0, 0, 0, then that formula simplifies to a good old x squared plus y squared plus z squared equals r squared. And that's it. But I hope you can kind of appreciate just how natural this generalization is, right? I bet you could even figure out what the formula for a sphere in 4 dimensions is, or 5, or 6, or 7. Think about it. Ponder it, right? Here, I'll do this. Hmm. Hmm. Okay. um, all right, let's turn things up a tiny bit. What I want you to try is this, or we'll think about it and then we'll try it together. Show that this equation here is the equation of a sphere and find the center and radius of the sphere. So think about how you could do it for just a moment. All right, now say something out loud to yourself, to the wall, to your dog, to your cat, to your hamsters, to yourself. All right, and now write it down. Try to work it out. There's a technique that we need to use to figure this out. You might remember it. If not, ask one of your classmates, see what they say. All right, let's work it out together. So the technique that we're going to need to use to find the center and the radius in this case is the good old technique of completing the square. Completing the square. So here's how we're going to do it. I have the whole thing written out here. We're going to collect like terms. Well, I shouldn't say like terms. Maybe I'll say collect like variables. So first thing I'm going to do is I want to get all the x terms together and all the y terms together and then all the z terms together. And then we're going to complete the square 3 times. So completing the square on the x terms, completing the square on the y terms, completing the square, oops, a little too far, completing the square on the z terms, and then the 6 just hangs out until the very, very end. There you go. This is a perfect square trinomial. This is a perfect square trinomial. This is a perfect square trinomial, which means it factors into a perfect square, and we get this, this, this. Then we just combine all of the constant terms. Oops. Combine all the constant terms. We get 8, or sorry, -8, and we can just throw that to the other side. So this is the equation of a sphere that is centered at -2, 3, -1 with radius square root of 8, or 2 root 2 if you want to simplify it. All right. Okay, next. Here's a question for y'all. What region in space, 3 space, is described using the following inequalities? 1 is less than or equal to x squared plus y squared plus z squared, and that's going to be less than 4, but also z has to be less than or equal to 0. So again, think about this one. Try to think about what this region could look like. Use your intuition for something that looks like this, and kind of what this looks like. Think about it for a minute. All right, now say something out loud. What could this possibly be? How would you describe it? All right, now write it down. Write down what you're thinking. See if you can draw a sketch of it. We'll have a picture in just a minute, but see if you could draw a sketch. Sometimes to draw a sketch, it helps to start by drawing the axes a little bit like this: x, y, z, and then see if you can kind of like do a rough sketch of it. Okay, so here's the first thing. This inequality is basically telling you that we're talking about a sphere, but it's an inequality, so we're not talking about a sphere. It's almost like we're talking about a ball, except the inequalities are on both sides. So if I ignore part of it for just a minute, there we go. This piece, that's basically the sphere centered at the origin, or sorry, the ball centered at the origin with radius 2. So we're not talking about just the shell. We're talking about the entire filled in ball. That's what this gives you. But we're not quite talking about the whole ball. We're also going to cut out the middle of the ball. So this is basically, imagine like a hollow ball, right? It's a hollow ball. The radius is 2 for the outer part of the ball, and then the hole in the side, the part that's missing on the inside, that's like radius 1. right? Yeah, hollow ball. There we go. Now, that's just what the first set of inequalities says here. This inequality adds an additional restriction. So not only are we talking about a ball that's got a hole in the middle of it, we're also going to chop it in half. So we're going to take that ball and we're going to chop it in half and only take the lower part of it. So this region looks a little bit like the half of a really, really round avocado with the seed removed. So if you've ever like cut an avocado and removed the seed, this is kind of what it looks like. There you go. And that's a nice figure, a nice diagram of it right there for you. There you go, the avocado. But it makes sense, you see, right? So here's the outer radius, here's the inner radius. We're only concerned with stuff that's between those two radii, and then we're going to go and just chop it right in half. All right. On that note, can't do it right now, but we're going to play. So for every one of these sections, we're going to have an associated activity related to it, and we are going to play. And that's where a lot of the fun occurs. That's where we're going to practice and talk to each other and learn about each other and figure out all of these cool things. But this is already getting a little bit long, so I'll try to cap things off here. Some of the lectures are a bit long. Some of them are going to be very, very short, but it all just kind of depends. In the first chapter, there's just so much preliminary stuff, so they tend to be a little bit longer. So I do apologize for that. So budget your time wisely. Remember to watch these lectures before you come to class, because then we will do an activity related to them in class. All right, that's it for today. I will see you next time when we talk about vectors. Have a good one.